the next topic of heat treatment of steel. Okay, which is nothing but when you heat treat a material. Okay, when you heat treat a material, what will happen in to its properties and phase changes, etc. That we will be seeing today. Okay, this will be the last topic for the first unit. And just a minute, I will connect the headset. Just a minute. Okay, am I audible now? Hello, hello, hello. Am I audible? Hello, am I audible? Hello, hello. Vedant,
Sir?
am I audible?
Yes, sir.
Okay. Why can't you reply? Vedant, where you went? Okay, Gauri Shankar, my screen is visible.
Yes, sir.
Yeah, good. Okay, so now we will be seeing about the heat treatment of steels, which is nothing but a combination of heating and cooling operation. So whenever we talk about the heat treatment, it is heating a material to a particular temperature for a particular time. Okay, for a particular time, and cooling it in one way or another. Cooling may be in any form. Okay, so the combination of heating and cooling operation, which is timed and applied to a metal. Okay, a metal or an alloy, heat it and cool it in a solid state, that will produce you the desired properties. Okay, first, for heat treatment, what you have to do it is, first you have to take the steel, and the steel will be heated to a some temperature, mostly above the critical temperature. Okay, critical temperature we have seen in the last class, mostly above the critical temperature, which will yield it to form the austenite. Okay, which will yield it to form the austenite. And the rate of heating is also very important. Okay, the rate of the rapid heating, slow heating, everything will be having an important desirable effect on the properties. Okay, desirable effect on the properties of the same. Okay, so when you talk about the highly stressed material, what happens is it will be heated slowly. Okay, it will be heated slowly, and it will be a stress free material. Okay, it will not happen, it will not yield to any distortion or any disruption or etc. Okay, so after heating, what you will do it is, after heating, the material will be cooled at a desired rate. Okay, the rate at which it is cooled will decide the type of heat treatment process, whether it is an annealing process or a normalizing process or a tempering process. Okay, so that is what heating and a cooling operation, combined heating and cooling operation to a metal, apply to a metal or an alloy in a solid state. Okay, in such a way that that will produce a desired property is called heat treatment of steel. Okay, so my voice is clear, right? Hello, hello, hello.
Yes, sir.
Yeah, okay, if any issues, let me know. Okay, Vedant, Vedant, are you there?
Yes, sir. Yes, sir.
Yeah, okay. So next is heat treatment. Types of heat treatment, as I told. In annealing, we have different types. In annealing itself, as I already told, the rate at which we are cooling, okay, after heating, the rate at which we are cooling will decide the type of heat treatment process. Okay, will decide as the type of heat treatment process. Okay. Now the first type of heat treatment process is annealing. Annealing is nothing but heating the steel or a metal or an alloy to a particular temperature, then slowly cooling it inside the furnace itself. Okay, after heating it in the furnace, slowly cooling it inside the furnace itself. That is in a good insulating medium. Okay, inside the furnace itself, it will be slowly cooled. The cooling rate will be very slow. Okay, the slow cooling will be generally continued to lower temperature, whatever the temperature may be. We need to the desired temperature, it will be cooled very slowly. Mainly when you talk about this annealing, the annealing will, what will do it is, since it is heated above the critical temperature and slowed down slowly, and as the rate of cooling is very slow, it will refine the grain structure. Okay, it will refine the grain structure. When the grain structure is refined, ultimately the grain boundaries will be reduced. Okay, grain boundary sizes will be reduced, which will prevent the dislocation to happen. Okay, which will prevent the dislocation in happen, which will ultimately strengthen the material. Okay, and it will also induce some softness. It will improve the properties also, electrical magnetic properties. Machinability is also, it will be improved. Okay, machinability also, it will be improved. Okay, so these are the important parameters why we are carrying out the annealing process. Okay, so after this, what happened is continuously heating. For example, this is a critical temperature line, and we call this as a A1 line. Okay, so at this point, if you heat it, so we are heating it up to this 133 degrees Fahrenheit. So if you continuously heat it up to A3 line, above this A3 line, that is upper critical temperature, the entire microstructure will be showing you the austenite structure. So when you slowly, that is what happens is, when you slowly start the heating, initially it will be having some perlite and some ferrite content into it. Okay. Then afterwards, the ferrite content will be increased and the perlite will break into austenite. So above the upper critical temperature, this is above this A3 line, if you heat it, ultimately this austenite will be completely formed, completely whole throughout the structure. This austenite will be formed. Okay. So that is what this heat treatment, how at different temperature. For example, if you see after this 0.8%, so this structural changes, that is from perlite to austenite, happens between zero point 0.2 to zero point 0.8. But if you see after zero point 0.8, ultimately there will be that it will be breaking down. Okay, after then it will be cooling. After this it goes to austenite, and after cooling it down, after cooling to the basic room temperature, it will again form this perlite and ferrite, but with the reduced grains. Okay, this is, see here, this is the original perlite and ferrite. After heat treatment, if you see, it is perlite and ferrites, the grains will be reduced. Okay, refining grain structures. Okay, that is what I told you. The grain boundaries will become smaller, which will prevent the dislocational motion, and ultimately the hardness of the properties or some mechanical properties will be improved. So these are the stages. First A, B temperature is being increased, and it ultimately increased to above the upper critical temperature. Then it is slowly cooled down to the normal temperature. Okay. So at the higher temperature only, you will be having the present of austenite, and then if it slowly cools down, it will be converted to perlite and ferrite. Okay. Okay. So mainly this refinement of the grain size will be happening above 50 degrees Celsius, above the lower critical temperature itself. This refinement of this refinement of lower critical temperature happens. Okay, this refinement of lower critical temperature happens. Just a minute. Yeah, refining of this grain size happen, and after heating it, ultimately more austenite grains. Okay, more austenite grains are formed, which on further cooling it will be transformed to perlite areas. No problem. In the very higher critical temperature, ultimately the austenite only will be formed. But if you cool it back, it will convert back into ferrite and perlite, which will give you a very coarser structure. Okay, which will give you a very coarser structure, and pro-eutectite cementite, by a network of cementite it will be formed, and this excess cementite will give you a brittle nature. Okay, will brittle nature. Full annealing cannot be a final heat treatment process. Still more heat treatment can be done in it. Okay, so if you done still more heat treatment, more thick and hardened grain boundaries will also result, but the disadvantage, it will goes to poor machinability, but it will go to poor machinability. So this is what, see here, in this up to 0.8 percentage, this we call it as hypoeutectoid steels. These things we have seen it in the last class itself. So the percent constituent continuously increases. So within this it will be pro-eutectoid ferrite. Before this, up to around 0.8 percentage, and above this percentage of the constituent, it will be a pro-eutectoid cementite. But here, up to this point, up to this constitution around 70 or 80, above that only you will be getting pro-eutectoid cementite, when it is a hyper eutectile cementite. Okay, sorry, steel. When it is hyper eutectile steel, you will be getting the cementite above 75, but ferrite you will be getting it from 0 degrees Celsius itself, but with lower percentage of carbon. Okay, so that is the main thing. So next, what is spheroidizing? Okay, spheroidizing is nothing but prolonged holding at a temperature. Okay, if you take a temperature, either it may be a lower critical temperature A3 line. Okay, this we call it as lower A1 line, or the A3 line at a particular temperature, if you hold the material at that particular temperature itself, or if you hold the temperature below a particular lower critical line or whatever may be, and heating and cooling it alternatively, okay, alternately, continuously heating cooling it above and just below the critical line, heating, what happens is we call it as periodizing. That is heating to a temperature above a lower critical line, then cooling it very slowly in the furnace, then heating it again, then cooling it back to the lower critical line, heating it, cooling it, heating it, cooling it, means you will be getting this periodizing. This periodizing cementite, which is shown in the figure, will be formed like this. Okay, the perlite and ferrite combination will be like this. Okay, this is what we call it as the microstructure. Okay, some microstructure. Then stress. There is also another type of annealing called stress relief annealing. Stress relief annealing is nothing but if you go for a machining operation. Okay, if you go for a machining operation, when you go for a machining operation, what happens is, yeah, when you go for a machining operation, what happens is, due to the machining operation of material removal, some residual stresses will be hold back in that particular material. So that hold the particular stresses which are hold back into the material even after the force is removed, even after the machining force is, sorry, even after the machining force is removed, that kind of stresses we call it as residual stresses. Okay, to remove that residual stresses, we can go for this stress relief annealing, or we can call this as subcritical annealing. Okay, it is usually carried out at a temperature below the lower critical line. Okay, this is a lower critical line. Below the lower critical line, we will be carrying out this stress relieving, this what you can say annealing, usually between 1000 to 1200 Fahrenheit. Okay, 1000 here it will be 1000 to 1200 Fahrenheit. Within this temperature, you will be heating it and you will be cooling it to just to mainly to remove the residual stresses which are hold up in the material even after machining. Next is called as process annealing. Process annealing is nothing but heating the material to around 1 to 1200 or 1300 degrees Celsius. Okay, 1200 or 1300 degrees Celsius, where it is, yeah, 1200 or 1300 degrees Celsius. Then after heating it, okay, up to this stage, after heating it, then we will be cooling it slowly. Okay, which is mainly used to soften the material, where the further recrystallization will not be possible. It will be also below this lower critical line only. This is lower critical line, AC1 line. Below that AC1 line only, it will be happening. Okay, it will be happening. Okay, this is also can be used, this kind of process annealing operation also can be used for this stress relieving operation also. So this is the temperature range. Okay, up to this it's called as process annealing. Usually 1100 or 1200 we will be going for this process annealing, and at 1300 degrees Celsius we will be going for periodizing annealing, and within this range 1400 to 1450 we will be going for full annealing or full hardening, and above that the ultimate is the normalizing type of heat treatment. We will study it one by one, no issues. Normalizing, next, normalizing is nothing but heating it approximately 1000 degree Fahrenheit above the upper critical line. See here, sorry, not 1100 degree Fahrenheit. Usually the, at this point if you take the upper critical line is at 1700, so up to 1800 we will heat it. So 100 degree above it we have to heat it, then followed by a cooling in a still air to room temperature. That is, within the furnace we will not be heating, we will be heating it within the, what you can say, we will be heating it within the outside in the room temperature, normal temperature we will be heating. So it is noted that for hyper eutectoid steels, here in this kind of medium, for hyper eutectoid steel, what happens is, what happens is that that upper critical temperature line will be having a dissolving cementite network. Okay, mainly this kind of study, okay, mainly this kind of study is used to necessary to make the system harder. Okay, to make the system harder, or to make the system more stronger steel than full annealing operation. Okay, the more stronger and more more stronger kind of thing, more stronger steel than the full annealing operation. So some application of normalizing may need still final heat treatment also. Okay, normalizing can be carried out to improve the machinability operation. Okay, so the increase in this cooling rate due to air cooling will be compared to furnace cooling. Compared to furnace cooling, it will be having some effect in the temperature. Okay, some effect in the temperature, microstructure or this transformation to austenite. So since the cooling is not carried out under the equilibrium condition, okay, still the cooling is not carried out under the equilibrium condition, the iron carbide diagram cannot be used to predict the proportion. Okay, cannot be used to predict the properties of this kind of steel. Okay, since which is done it in the room temperature. Okay, since which is done in the room temperature. Okay, here there is a less time only it will be taken for conversion of this pro-eutectoid constitution which is formed into a ferrite or a pearlite combination, okay, which may be an annealing or a normalizing stage. That conversion, okay, that conversion will take only a less time compared to the annealing operation. Okay, so here if you see, this is an annealed component wherein it will be having a very coarse lamellar pearlite. Okay, cementite fear is, okay, this the white color portions we call it as ferrite, and the black color portions we call it as cementite. Okay, so that pearlite and ferrite and cementite will be alternatively formed. Okay, which will be alternatively formed, which can be compared with the annealed one. Usually the 62% pearlite will be there and 38% ferrite will be there. Okay, so this will be the difference in structure. Here it will be somewhat coarser, and here it will be medium, and then still normal. Still you can find it. Still you can get finer structures also. Okay, if it is needed. Next is hardening. Hardening, as I told you, this it is nothing but a gamma to alpha transformation. Okay, we have seen what is gamma, what is alpha, etc. in the last 2 or 3 classes. That how we are going to convert that gamma to alpha. Okay, the transformation which is usually taking place by the process of nucleation and the growth, and it's time dependent. Usually when you see it, that cooling rate and time taken, okay, the time taken which is allowed for the carbon to diffuse. Okay, so that is very important. These two parameters only will be trapping the carbon into the solution. There in the heat treatment you will be getting an austenite. Here you will be getting a martensite kind of thing, which is also nothing but a super saturated solid solution of carbon. Okay, which will be a less dense than the BCC type of structure. Okay, in this type of structure, the two-dimensional unit cells are mostly equal, but the third is slightly extended because of the trapped carbon. The third structure, okay, the third structure may be slightly extracted, okay, extracted or distorted, which will lead to some, which will increase the hardness. Okay, which will increase the hardness. Here in this hardening, what you will be doing it is, we'll be having a quenching process. Okay, quenching process is nothing but what is that is quenching is drastic cooling. Drastic cooling means inside any quenching medium, the heat treated solid will be, just a minute. Just whether my screen is visible. Hello?
Yes, sir.
Yeah. So that two-dimensional, what I was, yeah, quenching is nothing but after heat treating, we will be taking the solid and we will be quenching it in the liquid medium. Okay, we will be quenching it in the liquid medium, which will form you the needle-like or acircular structure, which will be giving you a still more hardness or more hardened type of steel. Okay, more hardened type of steel can be formed. Okay, so that is what this hardening is. See here, this is usually the structures of this BCC. Okay, BCC, it will be having a body centered cubic structure, and in that body centered cubic structure there will be some carbon atoms which are present in the, what you can say, some carbon atoms which are present in the interstitial activities. Interstitial means in between the unit cells, some carbon atoms will be formed. So that carbon atoms, because of that induction of that carbon atom, hardening of the operation happens. Okay, hardening operation happens. This is the difference wherein this A units, this lattice parameter A will be changing with compared to the three types of structures. Okay. This is hardening. Okay, so depending upon the what you can say carbon content or the depending upon the heat treatment, okay, which you do, the martensite percentage will be varying. If you take 90% martens, 99 a 50 percentage martensite type of steel, when you increase the carbon content, the hardness will be rising from 30 to around 55. Similarly, if it is 80% martensite, means it will 33 to around 57 or 56, like that it will be varying. So as quenched hardness, okay, as depending upon, so as I told, it will be depending upon the quenching. Okay, just a minute. Okay, so it will be depending upon the quenching, and it will be depending upon the percentage of martensite content and even the percentage of carbon content in the material also. Okay, so this is the iron carbon diagram where you will be having wherein you will be having the carbon percentage, okay, from 0 to 1.8, and the iron percentage also 100 or 9. Okay, now what happens is here in the temperature it will be like this. Initially this is the lower critical line and this is the upper critical line. So when it is at a particular 0.6 percentage of carbon, and when it is at the same temperature, if it is heated, ultimately at around 850 or 900 degrees Celsius, you will be forming a fully austenite FCC. Okay, fully austenite FCC will be formed. And here this is what that is martensite looks like a hypoeutectoid steel. Okay, here in this portion it will be look like a hypoeutectoid steel, wherein the needle-like structure will be noted. Okay, needle-like structure can be noted. Okay, so when the steel is cooled rapidly after heating it to this fully martensite temperature, if it is cooled rapidly, a very hard martensite can be formed. Okay, this FCC austenite, which tries to change from FCC to BCC, a new structure called body-centered tetragonal will be formed like this. As I told earlier, a body-structured tetragonal structure. Already a BCC will be there. So along with that body-centered cell, a carbon atom will be getting attached to the interstitial activity. Okay, which will yield it to form a body-centered tetragonal type of structure. Okay, so this is what fast cooling from a fully austenite stage. Okay, the transform, what are the important characteristics of this hardening martensite temperature is hardening, what you can say, hardening martensite temperature is the transformation is usually dimensionless. Okay, it will not be having any changes in the chemical composition, but the volume of austenite will be formed, which will be having an impact in it. Okay, due to the shearing action, okay, there will be an impact in the volume of austenite. Okay, it will be changing that volume. If the volume changes, ultimately the crystal structure also will be changing. Okay, when the volume changes, ultimately the crystal structure also will be continuously changing. Okay, still it will yield to a what you can say a better kind of mechanical properties. Usually this transformation proceeds only during the cooling operation. After heating, only the cooling operation, that is, it will be ceasing off it, that the heat will be quite coolly ceasing off. Then the transformation of temperature, this transformation, that is from a particular structure to another particular structure, the transformation depend upon only in the decrease of temperature. Okay, how we are going to decrease that temperature. Okay, it cannot happens in a constant temperature. Constant temperature means it will become an isothermal transformation. Okay, so the amount of martensite which we can form it below the, what you can say, below a particular temperature or produced at the first is very small, then the number increases. Okay, near the end it will be continuously decreasing again. Okay, so that is what we call it as two temperature. The temperature at which it start to form the martensite is ms temperature. At the temperature at which the martensite formation is ended is called as mf temperature, is called as mf temperature. Okay, so these are the two important thing you have to note it. Okay, next is tempering. Next operation is tempering operation. Here the steels can be heat treated to a very high hardness. Okay, compared to the other heat treatment operations. Here in this tempering operation, here it can be heated to a very high hardness and a very high strength also. Because the hardening will be carried out with at a very high operating stress. That is, the component will be subjected to a higher strength and higher, which needs to be, which is a need to get a higher strength of the hardened temperature. Okay, mainly dies, knives, cutting devices, forming devices, and all will be tempered only, wherein we need a harder, very hardened structure to resist wear, tear, and deformation. So what happens here is, as quenched hardened samples, as we have seen in the last case, as quenched hardened samples will be taken, and it will be heat treated again to reduce the brittleness of the hardened steel. Okay, without lowering its hardness and strength. That is very important. So all the hardened steels are tempered before it is used. Okay, that is very important. After hardening operation, the tempering operation will be done to increase its brittle nature. Okay, to reduce its brittle nature of the hardened steel. Next, when the tempering is, the steel will be heated above a particular some temperature. Let us take it as A1 temperature and below the lower temperature and cooled below the lower temperature. What happens is the residual stress which is built up on it. Okay, the residual stress which is built up on it will be getting relieved. Okay, will be getting relieved, and the ductility and the toughness of the steel will be improved. Okay, so the hardness up to a particular temperature it will be increasing, then the toughness will be increasing. Okay, the hardness will be reducing after a particular temperature, but the toughness will be increasing continuously if you increase the heat treatment operation. Okay, heat treatment time. Okay, heat treatment temperature or time. Usually this temperature range will be from 400 to 800 degree Fahrenheit. Okay, as I told, mainly to get higher hardness and higher toughness. So for this hardness and wear resistance, what you will be doing it is that you will be heating to a below of 400 degrees Celsius, and for tempering we will be heating it for above 800 degree Fahrenheit. Okay, so only if you need it for stress relieving operation means by 400 or 900 Fahrenheit it is almost enough. Okay, so that martensite, how much martensite which is formed will be completely responsible for the hardness mechanical property. Okay, hardness property. Here if you see it here, it will be clearly understood. See here, there are three types of structures. So when you heat it up to only 100 degrees Celsius, you will be getting a fine perlite form only, wherein the hardness will be increasing from 100 to around 300 degrees Celsius. But if you take a material of tempered martensite, okay, tempered martensite, and if you heat it from around 300, okay, 0.2% to around 1% of carbon, the hardness will be ranging from 300 to around 500. Martensite will be still more further. So what it is clear is the amount of see what you can say the martensite present in it will yield the higher amount of hardness in it. Okay, will be yielding a higher amount of hardness in it. Okay, so this is a very important tempering effect of carbon. Okay, so this is what I told you, heating between the range 450 to 750 will be yielding you the martensite, and that martensite will be yielding you the hardness. Okay, will be yielding you the hardness. Some black mass structure will be formed which we call it as torsite. Okay, which we call it as torsite. Yeah, which we can call it as torsite, trostite. Okay, trostite. That trostite, that black mass structure, which is formed out of carbides. Okay, which can be viewed through an optical microscope, will be giving you a comparatively a better yield. Okay, a better yield of hardness. Okay, so when you temper the same thing, if you take it as a tempering around 750 to 1200 degrees Celsius continuously, again it continues the growth of cementite particles. Okay, again it continues the course of cementite particles, but the ferrite matrix which is being included in it also will be formed. So here it will be yielding you the sorbite structure. We call this as a sorbite structure. So the changes in the microstructure will be very gradual, and the product of tempering will be a tempered martensite. Okay, will be a tempered martensite. Okay, so this is what, see here, this will give you a clear picture. So when you take an austenite and at the rate at which it is cooling, for example, if you take a rate at which cooling from 0 to 1 degree Fahrenheit per degree per second, it will be forming you a coarse perlite. Okay, a coarse perlite. Okay. Similarly, at around 20 means medium perlite. At around 60 means fine perlite. Similarly, at rapid cooling, and rapid cooling means it will yield around 40 to 60. If it is formed martensite, it will go to a maximum of 64. Okay, it will go to a maximum of 64. Okay, this is what the structure is. Okay, this is what the main transformation structure is. When the cooling rate is 30 to 40 and it is hold and 1200 to 1300, it will be as periodized cementite will be formed, where the RC value will be only 5 to 10. But sorbite, as I told, sorbite or trocite or black martensite is formed comparatively it will be having a better hardness value than the other thing, the other things. But the temperature range up to which, for example, if you take this martensite, it is heated up to 400 degrees Celsius to form the black martensite. Okay, which will be nothing but a formation of epsilon carbon and the low carbon martensite combination. Okay. Similarly, when you heat it for 400 to 750 degrees Celsius, the cementite particles will become again smaller. Okay, the cementite particles will become again smaller and it will retain its original austenite structure. Okay, similarly, sorbite also will become small and round and it will yield you a better ferrite kind of compounds. So this is a tempering summary. Okay. Next is bainite. Okay, bainite. Bainite is nothing but when austenite, if you take, okay, when you take an austenite and if it is cooled further, okay, if it is cooled past a particular temperature, whether it is longer or thermodynamically stable or whether it is equilibrium or not, okay, when it is continuously cooled past than its temperature, than whatever it is needed, if it is continuously cooled, it will it will yield to another formation of a non-laminar structure. Okay, a non-laminar structure will be formed which will be comparatively rich in ferrite. Okay, which will be rich in ferrite, which will be consisting of a cementite and dislocation. That is, see here, this portion will be yielding to a bainite. Okay, so below the lower critical line, if you form this portion, will be yielding you the formation of bainite. So here in this bainite, what happens is it will be consisting of a cementite plus a rich ferrite. Okay, plus a rich ferrite. Okay. So ars tempering is another type of heat treatment process. Here in the ars tempering process, what you will be doing it is, we will be developing a structure which will be completely 100% binate. Which will be completely 100% binate. It will be how it is done is it will be what we will do it is, we will be heating it to a temperature. Okay, we will be heating it to a temperature and then we will be cooling it rapidly in a salt bath. Okay, in a salt bath we will be cooling it. So when you cool it in the salt bath, ultimately a formation of bainite formation between this ms and mf, it will be happening. Okay, between this ms and mf the bainite formation will happen, which will make the piece which is left out in the bath transform to bainite completely. So the steel directly gets transformed to bainite from austenite with no intermediate changing. Okay, that is the very important thing. Okay, the steel directly the steel directly gets transformed to bayanite and it is fully hardened to martensite steel. Here the tempering is a complete heat treatment phosphate and no reheating is required. In the previous case, a reheating is required, but in tempering, a reheating is not required. Okay, are you following? Hello, hello.
Yes, sir.
Yeah, yeah. Okay, next is Mar tempering. Mar tempering is also a heat treatment process only, but here what you will be doing it is, we will be heating it to an austenizing temperature. Okay, you will be heating it to an austenizing temperature and immediately we will cool it to using a salt bath. Okay, this what is the advantages of this is, it will make the surface and the, what you can say, the center of that bath, okay, this region, center of that region to be more comparatively have the same temperature. Okay, usually we will be doing air cooling to room temperature and then following it in the solid liquid bath. So Mar tempering also will be minimizing the residual operation and it will be reducing the danger to distortion or cracking also. Usually the heat treatment will be completely tempering the martensite to a comparatively a desired hardness, okay, compared to the other process. Okay, so with this these are the things of various types of heat treatment process. Okay, next is isothermal transformation diagram. Okay, isothermal transformation diagram. Just a minute, I will drink some water. Just a minute. Just a minute. So isothermal transformation diagram. Okay, what does it require? What does it say? So this isothermal transformation diagram also will be yielding you the various phase changes only, but at a constant same equilibrium temperature. Okay. So how we are going to do it is, first step is we have to take a large bar of sample, and from the bar of sample we have to cut a large number of samples. Okay, we have to cut the large number of samples, and from that large number of samples, what you have to do it is that sorry that large number of samples should be smaller in order, and it should easily react to change in temperature. Okay, whenever there is a change in temperature, it should be easily reactive. What you will be doing it is, we will take that bars which is which is cut into smaller bars. We will take that sample and we will be keeping it in a molten salt bath. Okay, at a proper austenating temperature. Okay, so now if you take a steel, the austenating temperature will be around 1425 degree Fahrenheit. Okay, 1425 degree Fahrenheit. So what happens is, if you take this 1400 degree 25 Fahrenheit, and if you cut the sample and if you keep it in a subcritical temperature of molten bath around 675 degrees Celsius, each you have to place it in that temperature for a particular time, prolonged time. Then after varying the time interval in the salt bath, what happens is, each sample will be quenched. Okay, each sample will be quenched, and that each sample will be subject in the cold water will be forming a iced brim. Okay, it will be forming a iced brim. So that after cooling, each sample will be checked for hardness, and it will be studied microscopically. So after studying it microscopically, okay, after studying it microscopically, so the what happens, okay, what happens is the important thing. Okay, how it is done, how the various operation happens, okay, how it is being compared. Okay, everything will be, we will be studying it, and from the data which is being studied, we will be drawing a diagram. That diagram is called as isothermal temperature diagram, and we call it as triple T diagram. Okay, this is what, right? This is the molten salt bath. Okay, molten salt bath. So different temperatures. Okay, different temperatures at which it is heated, and for how much time it is being done. Okay, how much austenite, perlite, and martensite is formed. Okay, how much temperature? 100% it will be perlite. At this stage, at this point, it will be 25% austenite and 75% perlite. Here it is 25% martensite and 75% perlite. Okay, 75% perlite. So this is the case. This is the isothermal transformation diagram. Here the martensite is formed from the austenite. As you already know, martensite is formed from the austenite in a very instantaneous form and at very low temperature. Okay, and at very low temperature. If the another fact is, if the austenite is formed at a higher temperature, which is stable at a room temperature, this rapid cooling will be yielding to a change of another product. Okay, it will be yielding to a change of another product, which will yield the formation of perlite. Okay, that perlite will be drastically, will become no issues with, if it is drastically quenched, or there will not be any perlite to change. Okay, so that is the main thing. So this is the isothermal transformation diagram. That is, for up to particular time you heat it or you can cool it, then at a particular temperature, the time temperature difference and how it is changing. Okay, how the phase difference is changing. That steps is very important. It is steps is very important. Steps involved in what you can say steps involved in developing a isothermal transformation diagram. Okay, this is another isothermal transformation diagram for eutectoid steel. Okay, eutectoid steel, a nose-like structure will be formed, which will be yielding a path-like structure, wherein the formation of austenite, ferrite, and cementite can be influenced. Okay, austenite, ferrite, and cementite can be influenced. Okay, this is what I told you, the transformation of a perlite to a bainite structure. Here in the perlite and bainite structure, where there will be a growth of martensite and cementite. Okay, initially it will be in a nucleus form. In that nucleus form, an alpha particle will be coming and inducing, which will yield to a formation of side nucleation. Okay, which will yield to side nucleation, and it will continuously go with up edge growth. Okay, It will be continuously go up with the edge growth. When it is upper bainite means, see, this is a perlite form of transformation. When it goes to an upper bainite, it will be enriching. Okay, it will be enriching, and A type, B type ferrites will be continuously formed with stringers introduced inside it, which will yield to form an austenite. Okay, which will yield to form an austenite. Okay, so this is a lower bainite structure. Okay, this is a lower bainite structure. So this is a cooling and cooling curve and IT diagram. That is, after heating to a particular temperature, if you cool it from that same temperature, what happens? Okay, if you cool it from a same temperature, what happens is the question mark. Okay, so that if you cool it from a particular temperature and the rate at which it cooling, it will yield to the formation of different types of structure. If you go up with this type of cooling, it will be forming a, at this temperature, if you going, it will be going for a coarse perlite. It will be forming you a coarse perlite. When you go it at this temperature, you will be forming it as a medium perlite. Okay, medium perlite, and then 5 perlite and cemented fahrenheit upper bainite. So depending upon the cooling curve, depending upon the hatched portion on the cooling curve indicates the transformation. This hatched portion, so along the transformation region, okay, this transformation region, which will be like a path, this transformation region will be yielding you the transformation from austenite, ferrite and cementite to any other combination of perlite and ferrite. Okay, so mainly there are different micro constituents will be there. Okay, micro constituents will be there. For example, if you take a spheroid, okay, it will be a combination of alpha ferrite plus ferrite carbide. Okay, alpha type of ferrite plus ferrite carbide. All the first four categories will be a alpha type ferrite and ferrite carbide only, but the name will be different: spheroid, coarse spherolite, fine perlite and bainite. So what happens is, the relatively small ferrite carbide particles here will be getting distributed in this alpha ferrite matrix. Okay, will be getting distributed in this alpha ferrite matrix here in this kind of type of structure, wherein which will be yielding you a soft and ductile material. But here what happens is, in coarse perlite, layers of alpha ferrite, one layer of alpha ferrite will be there, then ferrite carbide layer will be there, then alpha ferrite, ferrite carbide, like that, layer by layer, this alpha ferrite and ferrite carbide will be arranged. Okay, it will be also yielding you a harder and a stronger material, but it will not be as ductile as this purite. Okay, it will not be as ductile as this purite. Okay, it will not be as ductile as this purite. So, but if you take a fine perlite, what happens is, here also alternating layers will be there, but here it will, this also will yield you a hardened and a stronger perlite, but it will not perlite. Okay, but it will not be as ductile as this coarse or fine perlite. Here what happens is, this very fine. Okay, here in bainite what happens is, a very fine ferrite carbide particles will be there, which will be distributed in this alpha ferrite matrix. Okay, so that the harder and the stronger, finer perlite will be formed, which will be yielding you a less harder martensite. Okay, which will be more ductile than the martensite, ordinary martensite. Okay, but when you take a tempered martensite, very smaller ferrite spear-like particles, here fine spear-like particles, here it will become a very small ferrite carbide spear-like particles will be formed, which will be distributed in the alpha ferrite matrix. Okay, but it will be strong but not as hard as this martensite. So as I told, in the martensite only a needle shaped grains will be formed, which will be yielding you a very hard and a very brittle type of structure. Okay, this is the region at which, okay, this is the region at which the martensite, a critical region around which the martensite will be formed. Okay, the martensite will be formed. Okay, this is a ternary phase diagram. Ternary phase diagram is, if you take a metal or an alloy, if you take a metal or an alloy, and if you take three metals to mix and form that alloy. Okay, if you take 30 percentage of C, okay, 30 percentage, what you can say, yeah, yeah. If you take this point, okay, from the point we can analyze the percentage combination of each. If you take this point, 20 percentage of A. Okay, opposite is A. 20 percentage of A, and here it is 20 percentage of C, and here 1, 2, 3, 4, 5, 6, 60 percentage of B will be there. Okay, 60 percentage of B will be there. So correspondingly, the opposite structure, opposite side component will be taken. So whatever point you can take, we can analyze the percentage of each constituent from this ternary phase diagram. Okay, so usually what they are saying is usually the engineering alloys will be consisting of more than two alloying elements. Okay, so since it is not possible to represent more than two alloy element in a single graph, we will be going for this ternary phase diagram, which will be a function of temperature. Okay, which will be a function of temperature, which is one of the most important data to take the isothermal readings. Okay, so the construction lines will be showing in the upper part of the figure, and calculating the phase composition will be shown in the lower part of the figure, like this. Okay, see here, I will show it. So that construction lines is very important, and the phase compositions will be having some percentage of A, B, C, depending upon its structure diagram. Now, if you see this ternary phase diagram, a tie line diagram can be drawn. Okay, these things we have seen it in the last class itself. It is eutectic, means a liquid is transferred to alpha plus beta. Here in eutectoid means an alpha is converted to solid 1 plus solid 2, beta plus gamma. Similarly, in peritectic, okay, here structure you can see liquid is equal to alpha plus beta. Here alpha equal to beta plus gamma. Here this alpha plus beta, alpha plus L will be yielding you beta. Similarly, alpha plus beta will be yielding you the gamma, which is nothing but peritectoid. If it is monotectic, what happens is L1 will be yielding you alpha plus L2, and L1 plus L2 will be yielding you alpha. So this is a phase diagram characteristic for each reaction, what happens and what is the corresponding phase reaction characteristics. Okay, so this is another example for ternary diagrams. Okay, wherein at a particular point, for example, if you take this point, it has around 41 percentage of A. This length is 41 percentage. Okay, 41 percentage, and if it is go to C, it is around 26, and if you drag it to B, it is 33. Okay, corresponding percentages will be there. Okay, for every diagram, if you see at a particular point, if you take corresponding weight of A, B, and C can be calculated. Okay, so these are the isothermal temperature diagram and the ternary phase diagram. Okay, so what we have studied it in this first unit is it's all about the phase diagrams. Okay, it is all about the phase diagrams and how it is being changed.